Words. We'll get it. There we go. All right. So kind of all the way down here, got a bunch of different data sets we'll use today. Keep using that same do file. Going to go off the same slides. So you've got that set of kind of sample or practice questions. So the next quiz. Oh, I have it. So the next quiz will kind of, I've got related to these practice problems. I'll get posted after class today. Okay, so that'll be due a week from today. So you have a week to kind of get that quiz done. I'll also get it posted up the next problem set. So I was hoping to get it up yesterday. I'm making some changes to it based off what we've done in class. I still want to kind of see what we do today, and then I might alter a question or two. So I should have it posted after class before I leave today. If not, early in the day tomorrow. I'm going to have it set to be due on that Tuesday before the exams, not next Tuesday, but the following Tuesday. So you have a decent amount of time to work on it. We haven't covered quite everything. We've covered a pretty good majority of it. So I would start working on that early. All these problem sets, like by the time we get to the end of the material covered for them, we're probably a couple weeks removed from like question one, right? So starting these early is going to be helpful. I've also noticed, so you go to the files tab here under problem set one, I posted what a good solution file or good kind of, I don't know. Let's see. Download this. Oh, I don't want to do that. So I want to open it up here. Forgot to do this before class. So go to downloads. I'm going to drag this onto my OneDrive. So maybe. There we go. Well, just throw it in there so I can find it. So let's go back to the do file editor. Open that up so you can take a look at it. You should be able to open it up once you download it on your computer and put it into your OneDrive. Did not move it there. Nope. Oh, where did I put it? Should be right there. Let's try it one more time. Okay, so it's still in downloads. I just want to move it over to here. Okay. So it should be underneath there. Oh, maybe it's because I might have to reopen this. I did it ahead of time. Let's see. OneDrive, Spring. It's not showing up. Might be because I moved it after I opened up Stata. So let's try this again. So let me try to reopen this because I think it's worthwhile for you guys to see. I can kind of point some things out here. Some of the pitfalls that I noticed on the first problem set that I don't want to see happen on the second or the third. So the second problem set was due today. I might be nice and extend the due date to be the end of the day tomorrow. Okay. So if you need any last minute changes you want to make after I kind of go through this, you can kind of make those and get that uploaded by the end of the day tomorrow. I'll change the due date as soon as class is over. So I want to make sure I reiterate some things. Why is this not showing up on my OneDrive here? That's okay. I think I might have it. Oh. Somewhere else. It might just be because it's taking some time to download us. Let me see. God, hold on. Here we go. There we go. Looks something like this, right? So you'll notice like in certain questions, if I ask you for the mean, you need some code to figure out what it is, right? Like, I mean, I guess you can technically take this data set and do it all by hand if you want to. It'd take you forever. The sum command will report to me what that mean is. However, as we progress, we're going to have this state output, and there's not just one statistic, there's tons of them. So just because you know how to put the code in there and mimic something when you click, doesn't tell me you know how to find what statistic I'm talking about, right? And in fact, maybe you'll have to use multiple statistics in that output to calculate something else. So you need to use the sum command, but then also use comments or a Word document to somehow identify what that mean is, right? I don't know that you know where to find that in the output if you don't tell me what the answer is. So simply having this command would have not earned you full credit, right? That is what one way you could use to find the mean. But when I'm asking you for the mean, you need to report what that mean value is to me, right? There's plenty of code that will give us data output, but you need to identify from the output where the answer is or what the answer is, okay? So there's, in the solution file, notice there's multiple ways to do this. I could have created a new variable. I could have then found, okay, what is the value of this new variable? It should just be the same value for every observation. It should be equal to the mean of GPA. I should report to you whatever, or you should report to me what that value is. You need to identify what it is. Just as you're creating it, right? You still need to state what the value is, right? And this will be more important as we kind of progress. For the first assignment, it might have seemed kind of easy on some of this stuff. It's very easy to quickly identify like where the mean is in this output. But as we kind of progress through linear regression, it won't be as easy. So I've got kind of this solution file. A lot of this, it's more than you would need. It's like multiple ways of doing the same thing. So even if you did it one way, you can look at the solution file and figure out, okay, there was some alternative ways I could have used to do this, okay? Also, to reiterate this, anytime I'm giving you a problem set, what I would do, like for example, for that second problem set, let's see, it's linear regression. So I would use that simple linear regression file we've been using in class. Anything that I ask you to do, there's probably a good example of it somewhere in this file, just with different variables, right? I'm seeing people do things like run the sum command and then use our mean to figure out the mean. You can do that. There's much more complicated stuff you can do. Have I shown you how to do that in class? Have I, in any of this, you can look through all the old do files. Do I ever use this R? So do you think I expect you to use it on the problem sets? No, right? Anything I ask you to do, I'm giving you in these do files. You can, if you really want to become like an expert in Stata, I guess you can go and find, however else you're finding all this stuff. I don't know what resources you're using. There are more complicated ways of doing it, but I'm not asking you to do that, right? So anything I ask you to do will be somewhere in these do files that we're using in class, okay? Now it's not, you use this correctly if you were able to like, I think it's display, and then you displayed the mean of whatever the last. So this is where I don't want to go into the explanation of exactly what this does, because it's a little complicated, and a lot of you who try to use it used it incorrectly, right? Because what it does is it pulls from the last time you use the sum function. So if you want to use this display R mean later on, it's going to pull the mean of some other variable if you've used the sum function again. So I didn't want to go into all of that. I wanted to keep it simple, which is why I didn't discuss it at all. So there are ways, more complicated ways of doing it. But if I ask you to do something, you should only have to use whatever we've done in class, okay? So I'll extend that due date on the second problem set, give you a little bit extra time if you were kind of finishing up, putting some finishing touches on it. You can submit it by the end of the day tomorrow. I'll also get that third problem set up there. So it'll, if you're done with the second one, you can start in the third. Once again, for this third one, instead of this regression file, I would have opened this multiple linear regression. I think week 6 is going to, I think we have 2 files for this one. There was a week 5 and a week 6, but use the do file since the last do file, the last regression file, to kind of use it as good templates for how to attack that problem set, okay? And that's why I add things like all these comments in the stuff we do in class, so you can go back and try to figure out. I think there was one in the second problem set where I asked you to standardize a variable. In the regression file, I put in the comments like, this is how you standardize a variable. And it's different variables, but it's the same process, okay? Is that any questions on that before we dive into the material here? And come ask me questions. Like, it's a lot, I can't stress enough, like stop by during office hours. A lot of you, a couple of you do, like I'll work through a lot of this stuff with you. I want you to get good at using Stata because I know that how useful it can be once you get out of here. And actually on my way over here, I will try to take a picture and get it up on Canvas as an additional announcement. I don't know, many of you might be like, I don't want to do that, whatever, waste my time. There's some free class I saw a poster for where you can take like a free course in Python, which is basically R, which is kind of just a different data management program. You can do a lot more than data management with it, but it's like it's the industry standard, right? Kind of universally used data management program. So it would be something that's probably pretty useful to have some working knowledge of how to like code just a little bit, kind of do some of the stuff that we're doing in class here, but using R or Python. It's really the same programming language. Okay. So I'll put an announcement up on that just in case any of you are interested or curious about that. But we left off thinking about multiple linear regression. And we were looking at kind of this revenue data. Today, we're going to focus on this kind of traffic stop data. It's going to be a lot of the same things we talked about last class, just in a different context. And I'm going to sprinkle some additional things in there. Okay. So, oops. So if I'm thinking about, did I skip a slide now? So I had this data set, and it was like all these traffic stops, and I think it's from Houston. It says it's a large city in southern Texas. I'm pretty sure it's Houston. But I might want to identify like whether or not there's discrimination going on in the issuing of tickets, right, these traffic stops. So we said last class, what can I do? I can include multiple dummy variables. Now here, if I want to identify discrimination, I'm going to include dummy variables for what the driver's race was. Okay? So if, for instance, the driver was identified as being black, this would be a 1, 0 if not. So what would the interpretation of beta 2 be here? Now this is also where we talked a little bit before about we can also use an indicator or dummy variable as our dependent variable. So what is the units of a dummy variable if it's our dependent variable? Changes in it would be changes in what? So it can only ever be 0 and 1. So if it's moving from 0 to 1, there would be changes in the probability it belongs to the one group. And here, what would belong to getting issued a ticket, right? So beta 2 is going to say, okay, well, I have a dummy independent variable. So how do I interpret a change in that? A 1 unit change in the independent variable here will be going from the 0 to the 1 group. So being a black driver relative to the 0 group, which group do you think I probably left out here if I'm trying to identify discrimination? White drivers, right? So this is where if we have multiple races, we would have multiple dummy variables. I need to leave one out so I have a comparison group. What is that 0 group? If I tried to include a dummy variable for every single race, what issue would I have? Talked about it last class. Perfect. Starts with an M, multicollinearity, right? So I need to leave one out. I left out the white drivers. Now all of my coefficients should tell me if they're positive, that race is more likely to be issued a ticket when they're pulled over. That would be evidence that maybe I've got some discrimination going on. Okay. Now, not only is that the interpretation with multiple linear regression, what else do I get to throw on to the end of that statement? So it would be, this is the predicted change in my Y variable or the predicted increase in the probability someone's issued a ticket if the driver is black, comma, holding everything else in this regression constant. So here I only have driver's age. We'll throw in more later, but it would be holding the driver's age constant. Here's the effect or the change in the predicted probability of getting a ticket if the driver is black. Now, that's a more powerful statement. And if I start including more and more variables on the right-hand side, I get to hold more and more things constant. That statement becomes more and more powerful. Okay? So just to kind of look at some output, and I'll kind of show you how we do this. So if I did forget here, and this is where if I forget, kind of screws it up because it kicked out other group, right? So this was like, unidentified. Like they didn't have an identifier in terms of race. So this was going to be the group that gets kicked out. But that's okay because I can still identify if there's discrimination going on. So I didn't control for anything else yet, right? I just included these indicators for what the driver's race was. And Stata recognizes I have a perfect multicollinearity problem if I include every race, so it kicks out the other category. So here, what would be the difference in the predicted probability that a black driver is issued a ticket relative to a white driver. Well, I didn't leave out white driver here. It would have been good to if I had done this by hand instead of relying on stata, right? Because then I would have just had one coefficient. It would have been the coefficient on black driver. So what's the difference in the predicted probability a black driver is issued a ticket relative to a white driver here? What could I do?
The coefficient of black light by the coefficient of white.
Exactly. This is the predicted increase that they're issued a ticket if they're white relative to being in the other group. Here's the predicted increase if they're black relative to the other group. The difference between the two would be kind of comparing those two. Right? So it looks like it's about what? Close to about 0.03 higher, or if it's a probability of 0.03, it would be about 3% higher. So I have some evidence that there might be some discrimination going on. Now, the problem is, in this way, I'm comparing these coefficients. I don't have any, we haven't talked about how do I identify if there's a statistically significant difference between that, unless I leave one of those groups out in my regression. So, oops, if I instead left out white driver, which is what I did here, now when I'm looking at kind of this black driver coefficient, it's negative, and I can say, is that statistically significantly different from the driver being white, because I've now left out that variable? Well, now I can use that p-value that's reported to me in stata, right? And it looks like here I could say that black drivers are issued tickets at actually lower rates, right? At the 90 and what, 95% confidence level, not quite 99, holding everything else constant. So when we run these initial regressions, it might look like race is a pretty big, having a big impact on whether or not you're issued a ticket. But when I can control for all of these other things. So here I've got what was the gender of the officer, officer's years of service. I've got officer race dummy variables, driver race dummy variables. I've got this result of the stop. So remember last class I showed you, if you do have like a categorical variable, as long as it's like assigned a number, we could use that encode command. I can use the IDOT command. So the reason for the stop, well, you can imagine if I'm pulled over because I was speeding versus there's a warrant under my name, the likelihood I get issued a ticket or something might be a little bit different, right? So here I'm controlling for the reason why the traffic stop was made, officers, gender, years of service, the officer's race. Now the effect on if the driver is black looks like they're actually issued tickets at slightly lower rates or a slightly lower probability of getting issued a ticket. And I can say that's statistically significant at the 90 and 95% level. Okay. So just to kind of zoom in a little bit here. Oops, there we go. Who is actually kind of being issued tickets at lower rates? Well, it looks like black and Hispanic drivers are actually being issued tickets at slightly lower rates than white drivers, which might be counterintuitive to what we might initially thought, right? So here I would actually have evidence that there isn't discrimination going on towards non-white drivers. If anything, I might say, well, maybe there's some evidence that white drivers are issued tickets at higher rates. Also, what group relative to my white drivers is being issued a ticket at higher rates, holding everything else constant? Asian drivers here, there's a positive coefficient, so that would mean the predicted probability is actually higher. And like once I said, this is pretty powerful. Like we're controlling for all these, the reason for the stop, right? Office, all these other things. Okay, so this would be, one way. It kind of seems like it's a dumb example. It's just the issuing of a ticket, right? Including these dummy variables is a way we can start to identify discrimination. Maybe my Y variable is wages. Okay, identify wage discrimination using this, right? Hold constant the workers' years of experience, their degree, all these other things. Okay. Is there anything else? Oh, any questions on anything there before? So kind of a little bit of review of what we talked about last class. We're now taking, we can do all of this at the same time. We can control for a bunch of other variables and include these multiple dummy variables. Now, if we do, we have to make sure we leave one out so we don't have perfect multicollinearity.
So when you go back, R squared score is how do you wonder one?
Well, so we're explaining what? 11% of the variation in being issued a ticket. What would probably increase that a lot? Maybe if I had, I don't know, even driver's age, I think would probably explain a lot more of whether or not they're issued a ticket. Maybe, there's just a lot of other, you know, because race doesn't probably matter that much. The officers, you know, the reason for the stop might not matter that much. It's really whatever, you know, however you interact. Like there's things that we can't measure how you interacted with the cop once they pulled you over. I would guess that's like a huge reason of why you get a ticket or not at a traffic stop. We don't have a lot of other information. And so, yeah, there's still like 90% of the variation we can't explain. So we would want to be kind of cautious when making predictions using this model, right? Because we still can't explain 90% of the variation that exists in whether or not someone's issued a ticket. So it must just be we don't have variables that really matter. It's a good question. Any other questions before we keep moving here? But now notice, if I'm looking at, well, I cut it off. Here we go. If I'm looking at the regression where I only included race identifiers, no other variables, what should be true about my R squared? It should be even lower. Sure enough, if I just try to use the driver's race, what percent of the variation in being issued a ticket am I explaining? Well, the probability I'm explaining is 0.001, so 0.1%. So driver's race probably isn't explaining a lot of the variation whether or not you're issued a ticket. And then we kind of can include more variables. We get a higher R squared, et cetera. Okay. Any other questions on this before I keep moving here? I also, just out of interest, I kind of ran this, and there was also a variable in the data set for whether or not they were arrested. So I was like, oh, okay, well, this is like, you know, wage discrimination is a bad thing, right? But it could be that once you get the job, there's no wage discrimination, but they're less likely to hire you if you're of a certain race, right? So it might be that the discrimination is happening like earlier on. Same kind of thing here. Okay, if there's some discrimination going on in the issue of tickets, like that's not good, but what would be even worse? If your race changed the probability that you were arrested. So it's like a more extreme version of discrimination. So here, I did the same thing. I left out whether or not the driver was white. So here, if the driver is black, what's the predicted probability that they're actually arrested during a traffic stop? It goes up by 0.01 or 1% higher, holding everything else constant, holding constant the reason for the stop, officers' years of service, their gender, officers' race. So here I've actually got some evidence that, yeah, black drivers are actually being discriminated against, not in the issuing of tickets, but a more extreme version of discrimination of being arrested, right? And I can say that that is statistically significantly different from white drivers at what levels? My p-value 0, every level, right? So here we've got evidence of some pretty strong discrimination towards black drivers when it comes to being arrested at a traffic stop. Now, let's be cautious with these results, because why? What's another statistic up here that might make me a little more cautious of these results?
Low R squared.
My R squared is 0.06. I'm explaining 6% of the variation of why someone gets arrested at a traffic stop. There's a lot of other things that probably matter, right? If I had information on like their previous, arrests or something like that, if I can control for a lot more factors, I might be able to get a much higher R squared, and then the results would have more meaning. But still, kind of initial evidence, okay? So we've already identified this. I just blew it up a little bit so we could see the number, okay? I put some of the summary of the results, nothing crazy here. We probably have some omitted variables, so I wanted to go through. I think it's just good to see more examples of this. So we'll pull up in that do file. So I've got to go use my global. I put that traffic data up there, so that's the one we're going to open. So this is where, oh, I think I have it in a different file. That's why I put two globals, depending on what computer I'm on. I guessed the wrong one first. So there we go. So I've got that traffic stop data opened up. That should be on the main homepage of Canvas. All right. So this original variable of like whether or not they were issued a ticket, I actually had this weird variable, which was the result of the stop. And there was like a code book that came with it. And if the result of the stop was a 2, that identified that they were issued a ticket. right? So I had to create this whether or not they were issued a ticket variable. How do we create dummy variables? We said we generate this new variable that's equal to 1 if this statement is true, right? So we already kind of looked at this perfect multicilinearity last class. I can't use the same variable twice. That one's not, we won't kind of rehash that. Well, I also only originally had this driver race variable, which was a bunch of numbers. So each number corresponded to the driver being identified as a different race. Well, I can't really run this, like, it shouldn't be really treated as a continuous variable, right? I need to actually just use this information to determine what the driver's race was. So I looked it up in the code book and I created all these different dummy variables for what each number represented. And now I have multiple dummy variables that identify the driver's race. I then did the same thing for the officer. And I ran the regression with just driver's race. We kind of already looked at that in the slides, but just as kind of a reminder, oh yeah, it identified I had perfect multicilinearity. I kicked one of those out. Okay. So I'm going to come down here. These are the ones that we ran already. So whether or not they were issued a ticket, whether or not they were arrested. I included some additional controls. Once again, this reason for the stop, if I look at the data, so reason, it's just a bunch of numbers. Each number corresponds to some other, I forget, one of them is like speeding 0 to 5 miles per hour over, one of them is speeding over 20 miles per hour, all these different reasons, right? So that's what I was kind of wanting to control for. What was the reason to stop? I don't even have to know what each number represents. If I use this IDOT command, it'll create all these dummies variables for me, and it just controls for what the reason of the stop was. Right? And now it makes my coefficients a lot more powerful statements when I'm interpreting them. Okay? So let's go down here instead and think about this regression. So let's say I run a very basic regression where I regress whether or not a ticket was issued on whether or not the officer was male. So from this basic simple linear regression, what is this telling me? That if the officer is male, the probability an issue is a ticket is issued at a traffic stop is actually what? Lower, or the probability a ticket is issued is lower by 0.03. The probability goes down by 0.03. However, if this is somewhat older data, maybe I don't have as many police officers who are on the job who are females for 20 years, right? Maybe I have more male officers who are on the job because maybe it wasn't as likely, right? It was more of a contentious environment for females to kind of go into the police force in Southern Texas, if I'm looking at some older data. Right? I don't think that's a wild speculation there. So I'm going to think about, okay, what is the bias that would exist? So I know that we've done this already. I'm rehashing this because I'll ask you a lot of questions about this. So if I've got this regression that I'm running, and it's very naive. So it's kind of I think it was our male officer. Thank you. There we go. Now it should show up. There we go. Our estimate will include the true effect plus the coefficient of whatever variable we left out. So maybe here I'm thinking kind of the officer's years of service might matter. So it would be the covariance between that variable I'm looking at, whether or not they were a male officer, years of service, and then divided by the variance of that variable that I did include in my data set. Okay. So I can figure out what this is, what these different things are from Stata. Okay. So let's take a look at this. Right? So we'll come down here, and I kind of have this typed out if you're going back in the comments, but we just kind of wrote it out. So if I do run this regression, where I include years of service, what happens to my coefficient? It went from negative 0.03 to what? Oh, and I said, yeah, negative 0.001. So it went down by quite a bit, right? So we can kind of start to think about the reasons why. So if I did include years of service, what was the coefficient? Negative 0.012. approximately. So if I'm just kind of piecing this together, we said if we had run this naive regression where we didn't include years of service, if we did include it, the effect would have been, and now I'm already forgetting what it was, negative 0.0, about 1.2. Right? Now, the bias that would have existed would have also been a product of the covariance of officer being male with years of service. So I'm going to go back here. Now, first of all, if I have this result, what was the bias that was caused? Well, if it was negative 0.034, once I include years of service, it eliminates that entire bias. So if I have the data, I can run the regression and I know the bias was about what? It went from 0.034 to 0.001, so it was like negative 0.003. Almost the entire effect was being caused by the bias, right? In fact, here it looked like the officer being male had a statistically significant effect on whether or not a ticket was issued. Once I can just control for one other variable and eliminate the bias that existed from the officer's years of service, can I say that the effect of being male, the officer being male, has a statistically significant effect? Not even close, right? The p-value is 0.8, right? So how can I find the covariance? Well, we said we've got this command, which is I can use the correlate command between those two variables, the one I included, the one I excluded, and then kind of throw in this covariance that it gives me the covariance there. So if I go ahead and run that, that tells me 0.2165 approximately. That's going to be my covariance. The cross here, I could use the sum function or generate a new variable that was equal to the variance. But if I do this covariance matrix, the diagonals tell me the correlation or the covariance of officer being male with itself is just its variance. So if I want the variance of the officer being male, that would be right here, that 0.077, right? I could also do, maybe, there we go. All right, well, what did I forget? I don't want the standard deviation, I want the variance. So here I've got 0.0769, sure enough, it's the exact same value. It's just two different ways of getting the same value there. Well, now that I've got the variance and the covariance, so this will switch over for me. Why are my fingers not working? There we go. So this was 0.076 approximately, I think we just found, 69. And then the covariance was 0.21655. Now, if I want to determine what that bias is, without even running that regression, I can do that. Right? I've got all the components that I would need. Okay. So sure enough, if we go ahead and plug this in, we get that bias that's approximately negative 0.003, or the same thing as if I would have taken the difference between the regression where I included years of service and where I excluded it, right? So if I go ahead and kind of plug this in, I guess I can kind of verify. Let's open up, this is my calculator here. Sure enough, I get negative 0.033. Right? So the same thing as if I had just compared the regression where I excluded that important omitted variable and the one where I included it. Because as soon as I include it, what happens to that bias? It's completely eliminated. Okay? So I know that we've looked at multiple examples of this, but I'm really trying to focus on it for a reason, right? I definitely would expect to see questions like this on the exam. Yeah, or the quiz.
So the bias is the ones that omitted from the original regression.
Exactly. If I omit the years of service, the estimate that I see will not be telling me just the true effect. It'll be telling me the true effect plus something else. So when we ran the naive regression, the estimate I was seeing for beta 1
was like negative 0.034. Once I included years of service, now my estimate, it'll have the true estimate, but it'll eliminate this bias completely. Well, we just said, what was the value of this bias? Negative 0.033. So what should my new estimate be? Negative 0.001, which is what we found when we ran that regression, including years of service. So if I don't have the data, right, like a lot of the times, what does this look like? Well, maybe from my data set, I don't have years of service, but somebody else does. So they can kind of tell me what the effect should be and what the covariance would look like. And then I can kind of say, okay, how much bias was baked into my estimate? I didn't have years of service in my data set, but I know from other data sets approximately what it should be. Oops. Any other questions on that before? Yeah. Well, yeah. So use a different color here. If I didn't have the data and I just wanted you to put a sign to the bias, if you did include years of service, so what do you think the effect of years of service would be? If a police officer is on the job longer, do you think it's more or less likely they issue a ticket? I would think it's less likely. You're not trying to prove yourself, right? You can kind of identify like when drivers are being completely reckless and when maybe they were just something, I don't know. I would think that would be the story. You could probably tell a story the other way. If I'm on the job longer, I become an old curmudgeon and I just give everybody a ticket. So, I don't know. But so this one, I probably wouldn't be a fair game question because like I could see that going either way. If I ask you a question on the exam, it's going to be something where, honestly, as long as you would give me an explanation as to why you believe the sign is what it is, then I would count it correct. But I would try to give you examples where the sign is a little more obvious, right? But it's negative, and we actually found it's negative, so that makes sense. I said, if this is an older data set, the whole reason why I thought I might have a bias here on male officer is because it's likely that female officers weren't able to be on the job for 25 plus years if I'm looking at older data in Southwest Texas. Right? There just probably weren't as many female officers that got into it as early. So what would I think is true about the years of service, the correlation between that and whether or not the officer is male? Well, it's likely if they're on the job longer, they're more likely to have been a male officer, right? There weren't these roadblocks to kind of them getting into this career path, right? And then variance is always positive. So what would the sign of my bias be? Sure enough, we end up finding it was negative. Yep. Does that make sense? Any other questions on this idea before we keep moving here? All right. Give me 1 second here. I have something pulled open. All right. So the next thing I want to make sure we talk about today. Now come back to this. This is we've really hammered this enough. I might revisit this next week if we've got time. What I want to make sure we have adequate time for today is the idea of imperfect multicollinearity. So we've already talked about perfect multicollinearity. This is like if I try to use the same variable twice, or what was the example I used last class? Something like age and then like the number of years you've been of legal drinking age or something like that. Those are going to have a direct one-to-one increase. So let's think about some imperfect multicollinearity, right? So what's going to end up being true, I'll kind of lay out what happens. Let's say I have something like, well, a good one when we're looking at like wage data is if I have age and experience. So inherently, if I have more years of experience, what has to be true? Every year of experience I have, my age is going to have to be higher as well. However, it's not perfect multicollinear because I could have two individuals, someone who's 30, someone who's 35, and they could have the exact same years of experience. Right? However, every time I have one more year of experience, I know that that's inherently going to make that person's age one higher as well. So they move together, but they're not perfectly multicollinear, right? So what's going to end up happening, and we won't dive too much into like the nitty gritty of all this, But if I run this regression where I have two variables that are highly correlated, they're not perfectly multilinear, but they're close, right? When I think about this variable, I really could just rewrite it as a function of this other variable. Experience is going to be some function of my age. I can't have 20 years of experience if I'm only 35, right? However, it's not going to be every time I am 35, I have exactly 10 years of experience. So there's going to be some like additional error, like we don't have to worry exactly about this, but that one variable is a function of the other, okay? So age and experience is the one that I kind of always go to. What's going to end up happening if I run this regression, I can still get estimates for the coefficients of both age and experience. And in fact, I'm going to get an unbiased estimate of what those coefficients are. However, because they're imperfectly multilinear, it screws up my standard errors because like there's this additional error component that's kind of getting added in here, but it's not getting added to. So it's screwing up my standard errors of these estimates. Right? In fact, what it'll do is it always makes one of my standard errors too high. Now, I don't know which one. If these are two variables are imperfectly multilinear, it's going to screw up the standard errors of one of them, but I don't know which one. Okay. And I'll show you some examples of this here in a second. So let's say I've got something like this. Right? So if I run these regressions, and I can include other control variables as well. So I did that here just to show that to you. So let's say I want to predict wages with IQ, age, and experience. Seem like all good predictors. So controlling for IQ, it looks like the effect of experience is that it has a positive impact on wages. It's not surprising. And it's statistically significant at what? The 90 and 95% level. Age also looks like it's having a positive effect on my predicted wages. And it's statistically significant at every level, right? P-value is 0. Now, if I run this regression where I include experience and age at the same time, well, it should be that both of them look like they're statistically significant. Right? The problem is if I just talked about age and experience have this kind of linear relationship. It's not perfect, but it's linear, right? So if I then include them both at the same time, right? Notice what ends up happening. Well, I still kind of have estimates for age and experience. Now notice, if I include them at the same time, what did I do? Well, both of these coefficients looked like they were positive before. However, what would have been baked into both of them? An omitted variable bias. So once I put them both in my regression, I've eliminated that bias that would exist in both coefficients. So they're going to be different. This one wasn't a lot different, but it is different. This one is significantly different, right? Not only are the coefficient estimates different when I can include both of them, I said if they're imperfectly multilinear, one of the standard errors are going to be overly inflated. Notice what happens to my standard errors on the experience variable. They're 0.66, right? They're really high. So, anytime we have an imperfect collinear relationship, we're not going to be able to make a statement about statistical significance of one of those variables, right? We know that this actually shouldn't be the standard error. That standard error is actually going to be way too high. If the standard error is too high, what happens to our test statistic? So how do I find my test statistic? I take my coefficient and I divide it by the standard error. So if my standard error is too high, my test statistic will be low. My test statistic is low. What's happening to my p-value? It's going up, making it less likely I can reject the null. Okay. So how do I solve this? This is a problem, right? So we've got a couple solutions, right? So I'll outline them and then we'll jump over to Stata and look at a different example and kind of think about how we can solve this. Okay. So the first is don't do anything, right? When is this like an actual possible solution? Well, let's say I'm running this regression and I'm really interested in wage discrimination. So I have that same regression, but I also include like the individual's race. And those are the coefficients I'm really concerned with. Well, I still want to control for experience and control for age, but I'm not really as focused or concerned about their statistical significance. So I might just do nothing. I'm only going to focus on the coefficients I was interested in the whole time, which was these race identifiers. If I am interested in the coefficient for experience and wage or age, well, then I have a problem. Right? I can't just do nothing. Right? I know that the statistical significance is screwed up. I can try to think of if there are redundant variables. Sometimes I don't need both of them. Right? So like maybe age and experience are so closely related that I just only include one of them. That's also not a great solution because it's likely that even though they're close to the same thing, they, somewhat measure something different. So 2 isn't a very good option as well. So even if I know my standard errors of one of these variables is going to be inflated, what's another way I can combat this? So remember when we said we're calculating this test statistic, all my markers are dying on me. It's the sample coefficient divided by my standard error, right? But part of this standard error, this was like the difference between what? Our predictions, averages, squared over n minus 1. So if n goes up, what's going to happen to my standard error? We said as we take larger sample sizes, what's going to happen to my standard error here? The denominator is larger. I hope we know that what happens when a denominator is larger to a fraction, guys, right? So when my denominator is larger, that standard error is going to, so maybe if I wasn't clear, sorry. Right there. So if my standard error goes down, what's happening to my test statistic? If my test statistic is higher, what's happening to my p-value? It's going down, which makes it more likely I can reject the null. So even if I know my standard error is going to be screwed up on one of these variables, what's one way I can combat that? Get really big data sets, right? Then it's not going to matter as much, okay? So that is a possible solution if I can get the data, right? So as with most things, right, if I can just get more data, usually a lot of our issues are going to be resolved. Now, what I can also do, which allows me to use both variables, right? As long as I'm not super concerned with being able to evaluate both, but I want to make sure I have some good measure of how they're both impacting my y variable, I can create a new variable that is like usually some ratio of the two. So the age experience one is maybe not quite as good. I'll use this one where let's say I wanted to know the impact of maybe I do like life expectancy. Well, no. Maybe I want to do, what's a good one? Population and GDP and how they impact. Maybe I'm thinking about something like, I don't know, income, average incomes in a country. And I want to know how is that impacted by their population and GDP? Well, as the population gets larger, likely we have more resources. But as our population gets larger, we have more workers. What inherently is going to happen to GDP? It's going to go up. So there is some linear relationship that exists between population and GDP. So what might I want to do if I want to include both of them? Well, I know that if they're imperfectly collinear, one of the standard errors will be messed up. I could just kind of create a new variable, which is GDP per capita, right? Now, I only have one variable now, right? But I'm able to control for both GDP and population, and I've kind of gotten rid of the fact that my standard error on one of them is going to be screwed up. Now I'm just going to have one standard error associated with this new variable, and because there's no multicollinearity, I've only got one variable. I don't have to worry about any. Right? So we can transform our variables to be like ratios a lot of the time, and that'll also help solve that issue. Okay? So I've got a blank slide here. We've got an example. Maybe some of you will be a little more fun, right? So I'm going to use this. Oh, now I forget. Let's see. Did I move it? Yeah. Let's see if it's where I want it to be. See if I put it in the right folder here. Sweet. So I've got that on Canvas, that QB salary data. So I found this, it was like the total value of the quarterback's contract. It also had what their number of completions were. So how many passes they completed. It also had how many passes they attempted, right? So I'm going to run these regressions where I run each. So if I just run, the number of completions a quarterback has over a year. What's that impact on their total salary? I come up with some positive value, and it's pretty close to statistically significant. Not quite. P-value is 0.12, so I actually can't say it's statistically significant here. I then look at, well, what's the number of attempts? It also looks like it has a positive effect, but it's also just barely not statistically significant. Now, I know kind of inherently, like the quality of a quarterback is going to be like, how many times can they throw a pass to someone that can and they can catch it, right? Well, if I try to use just completions or just attempts, I can always increase my number of completions if I just throw the ball 100 times a game, right? So I know that like every time I have an attempt, or sorry, every time I have a completion, what did I have to have? Well, I threw the ball, so I had to have an attempt. Now, every time I have an attempt, I don't necessarily get a completion. So it's not perfectly multicollinear, right? So I'm going to run these two together. What should happen, we had p-values before of 0.12 on each variable. One of these should have a much higher p-value. In fact, what can occur is not just one variable is affected. That's kind of like the best case scenario. So if you go back to the slides, I think I said at least one of the variables will have their standard errors impacted. Here's a situation where what happened to the standard error on both? Well, if my p-values are higher, it must have been that the standard error on both of those variables was going up, right? Which decreased the test statistic and increased my p-value. So it screwed up my statistical significance of both variables now, right? Okay, well, I've got some solutions. One, I could do nothing, right? That doesn't really, do much for me here. I could choose one of them. If I'm choosing one of them here, and I'm thinking about like what's the quarterback's contract, I probably wouldn't choose like how many completions they have versus attempts. I think that gives me some better measure of their success, right? But it's not perfect. The next thing I could do is go out and get more data. Well, that's not always practical. Like I grabbed as much of quarterback contract data as I possibly that was out there, right? I can't just reinvent new years. I can't do that. So here, the only thing we're really left with is solution 4, which is I can transform those other two variables. So what's a statistic that you might often see in football, right? It's not the number of completions, or they don't talk about the number of attempts. A lot of the times what they'll talk about is the completion percentage, right? So what does that do? It essentially allows me to control for both of these things, right? If my quarterback is throwing the ball more, they're a larger part of my offense, I'm probably going to pay them more. However, I'm also only going to pay them more if when they're throwing it, they're actually accurately throwing it and someone's catching it, right? I have completions. So I do want to control for both of these things when trying to predict their salary. So I'm going to create a new variable, which is just the completion percentage. Now, technically, to give me a nice interpretation here, if I take the number of completions over attempts, is that a percent? So if I throw the ball 10 times, caught 5 times, that would be what? 0.5. How do I turn that into a percentage? Multiply it by 100. Might just give me a slightly easier interpretation once I get to the regression results. So I'm going to create this new variable of completion percentage. So now I can kind of take a look at it. All right, looks like it's between 0 and 100. That kind of makes sense. Now when I look at what's the effect of a 1% increase in completion percent, not a 1%, sorry. If the completion percentage goes up by 1%, what's the change in the total value of that quarterback's contract? Now I get that it's actually negative, which seems kind of weird, right? But it's now statistically significant because I've transformed both variables. I don't have my standard errors being impacted by imperfect multicollinearity. So I've solved my statistical significance problem here. Why is this negative? If I only have one variable on my right-hand side, what does that coefficient probably have a lot of? A lot of omitted variable bias, right? This is a very simple linear regression. I need to go out and try to find other controls, and every time I put another control in, it would eliminate the bias that exists in that coefficient estimate. Transforming the variables, it just solved my imperfect multicollinearity issue, which is impacting my standard errors, right? Not talking about that coefficient at all, okay? Going through this kind of quick, and I'm feeling I'm not getting a lot of, so any questions or clarification, anyone want? Yeah.
Don't know two variables that have perfect multicollinearity and you're running the data. What would be the best way to realize that if you didn't know that it was going to happen?
So let me think what I want to do here. What else exists in this data set? It's a good question. Let's do something that shouldn't. So let's do age and we could do. No, I forgot. So age and completions, right? So like being 1 year older doesn't inherently impact how many completions, right? It's not a direct linear relationship. Yeah, maybe being older is somewhat correlated with like my body's breaking down and I'm not able to do as well, but it's not like a direct one-to-one where we know that if you complete a pass, you automatically had to throw it. You had to have a completion, right? Or sorry, had to have an attempt. So if I run a regression like this, right, what am I going to find? Really low coefficient and really high p-value, because these two things don't look like they're that related. Now, if I were to run this regression on attempts and completion, every time I have a completion, what do I have to have? An attempt. So what should the p-value be here? I mean, I know these things are directly linear related, so it should be a p-value of 0, basically, right? So if I run this regression, sure enough, I get this p-value. So I should be really suspicious if I'm getting p-values that are basically 0 here. Probably is pretty could be I shouldn't say it's a definitive, but it's an indicator that maybe there's a linear relationship. And in practice, how do we identify this? Using our intuition, right? We kind of have to think about what these variables are measuring and whether or not there is a direct relationship. So for instance, it's not just that there's a covariance, right? That's like my example of age and the number of completions. Those might be correlated, right? But it's not inherent that when someone is 1 year older, they would have 1 more attempt or 5 more, whatever it is, right? So think of other examples where it was to be like, another one that's actually pretty good example of imperfectly multicollinear. Anytime I want to predict any y variable and I want to include both height and weight, if I'm 1 inch taller, I mean, obviously everyone's weight's different, but like the same person, if I'm standing here and all of a sudden I grow 1 inch, what's going to happen to my weight? It has to go up, right? There's more of me, right? As long as we're not looking over like a 10-year time period and I diet or whatever it is, inherently, just as someone is taller, they're going to have more on average, more space, right? So those two things would be probably pretty perfectly collinear. We would actually be concerned about including them as controls in terms of their standard errors might be messed up and their p-values be messed up. So we kind of have to use our intuition a little bit. So this is where it gets to be less statistics, more economics, right? We have to actually think about the intuition behind the relationships between the variables that we're looking at. But a good indicator is if you run a regression with just those two, you're going to end up with a really, really low p-value, right? And not only a low p-value, what would be a second indicator up here that tells me like, these are almost perfectly collinear. Look at my R squared. Should be almost 1, right? Or we're really close to it. I got 0.997, right? And that's because, yeah, every time I have a completion, of course, I'm going to have an additional. And if that's all I'm using to predict it, it's going to look like a 1-to-1 relationship. So an R squared close to 1 and a p-value really close to 0, from just like a simple regression of the two variables you think might be collinear, would be good indicators. It's a really good question, actually. Yeah. Yeah.
Just out of curiosity, the initial regression you have with regarding the completion percent, could you maybe include other variables that could reduce that bias?
Oh, for sure, right? I was just using this as a way to show you how to account for the collinear issue.
Yeah.
I know that the bias issue still exists when I run this regression. So what might I want to do? Age
Where is that? Oh, here, let's open the data set up. This is a good question. Oh, age. What else could I throw in here? Let's do touchdown, yards. So let's just do that here. So I start to include a bunch of other of these controls. Now what's happening to that coefficient? Still negative, actually, kind of surprisingly, but it's a much smaller negative value, right? Or I'm eliminating a lot of that bias that would exist between completion percentage and any of one of these other additional variables because they're no longer omitted. But yeah, I would probably want to try to go out and get as many other variables as I possibly could.
But the fact that we still have a negative coefficient means that we're excluding some very strong variable that should push it the other way.
Maybe. I would think from my knowledge of football, seems like that's kind of weird, right?
Yeah.
But, for whatever reason, if I'm controlling for all these other factors, maybe having a higher completion percentage is also what's one thing I haven't kind of controlled for here. Maybe I'm not running the ball as much, right? So maybe I'm getting to the issues of like quarterbacks can also have rushing yards. So maybe I want to include those as controls. So there might be just some variable I'm missing that's causing a large bias there. I can't think of what it might be off the top of my head since we included yards and touchdown, but yeah, there's likely some omitted variable that I just haven't been able. And I'm only up to, I'm getting my R squared a little bit higher, but not super high. Also, what's going to be an issue with these estimates? If I look at my sample size, it's only 43, right? So I likely want to, could be that I'm just getting a skewed sample. Could be that I just happen to have a sample that's, not kind of far on what they did on one of the far ends of the distribution. Okay. Other questions on anything there before we keep moving here? Let me think if there's anything else I want to say there. So we talked about that. Predicting. I think it's worthwhile doing this today, and we'll revisit it next week as well. So I keep using the same data set. So let's go here. Well, I've got it saved in this, so let's do this one. So let's go down here and open up a different data set, which we'll kind of use more next week on Tuesday. So I'm going to run this, clear out my old data. I'm going to use one of these free, and it might give me an error. Well, it didn't, right? So if it does give you an error, that's where we had the SSC install BQ. So I told you to do that a long time ago. It just kind of accesses all these free data sets. So this one's a smoking data set. So this is the number of cigarettes someone smoked, their education level, cigarette price, whether or not they're identified as white, their age and income, right? So let's say I run this regression. I'm like, great. I asked you to do a little bit of this in the simple linear regression, which is to start to make predictions. So some of you stopped by, you found this on a help file somewhere, I don't know, you looked ahead and you figured out how to do this, right? But if I run a regression, I can see these coefficients, right? I can by hand just compute, what is the predicted cigarette use of someone with 16 years of education. The average cigarette price in their state is $4 a pack. They're non-white, they're 35, whatever it is, right? I can go ahead, grab those coefficients, multiply them by the hypothetical values, and come up with a prediction there. Now, we also talked about what could I do to make a prediction for everyone. We could use that predict command. The problem is my hypothetical person might not be like an exact person in that data set, right? So if I want to make a prediction for someone who's not in my data set, what can I do? So anytime I run this regression, okay, I can use this display command. So once again, I've seen some of you already use this, right? But this is just a way to spit out a variable in Stata, right? Anytime I run this regression, it stores all of those coefficients behind the scenes. If I want to access those coefficients instead of typing out the numbers, I can use this syntax. So this is where I will introduce sometimes things to you down the road that I didn't earlier on because we got to walk before we can run. So we're starting to run a little bit here. Okay, so I run this regression. If I use underscore B and then kind of use these square brackets, I then tell it what variable I want. Underscore B is essentially that beta. I want the coefficient of my constant. I want to add to that
the coefficient of the first variable, education, times, well, if I want to make the prediction for someone who has 12 years of education, $5 average cigarette price, they're white, 30 years old, 45, I'm just going to go through and take each coefficient for each variable, multiply it by these hypothetical values. So the coefficient on education times 12, that'll get added into my prediction. The coefficient on cigarette price times the hypothetical value of $5, plus they were white, so that white coefficient would get multiplied by a 1, right? They're in that group that would be identified in this dummy variable as a 1. Take the age coefficient, multiply it by 30, and then take the income coefficient, multiply it by 45,000. Okay. So if I go ahead and do this, what this will do is it uses all of these stored coefficients and comes up with some predicted number of cigarette use here. I think this was, if I remember right, cigarette use per month. No, yeah, cigarette days used each month, right? 30 was like the highest, right, on average. Also, I think, yeah. So I could then come up with like a bunch of different predictions. Maybe I'm like, oh, yeah, but what if the person's only making 35,000? What if they, I don't know, are older? What would be my prediction? Well, there's my predicted use for them, right? So I can start to play around with these values. I can use those stored coefficients and come up with predictions really for any hypothetical person that I want. Yeah, so when I use this underscore B, it's similar to what I mentioned at the beginning of class when people are trying to use that R mean. Oops. Anytime I'm using some of this stuff, it's always going to pull from the last regression that was run. So like if I tried to do, I don't even have the data set open anymore, but let's say I tried to do not age, the completion variable. It's not going to be able to find it, right? It's only going to be able to use whatever results from the regression I just ran. Right? But they will be stored in there until I run another regression, right? So I can like run other lines of code. So like maybe I do some of this stuff. I can always then go back and still use those coefficients. So it's always stored behind the scenes temporarily until I run a new regression. Is that? Any questions on that before we keep moving? Okay. Let me think. We got a couple minutes here. So one assumption that we talked about, and I'll probably revisit this next week too, was we said in order for us to have this best linear unbiased estimate, the expected value of our error term had to be 0, conditioned on all the variables that we include on the right-hand side. So kind of an interesting way of some of the stuff we've talked about at looking at this. So let's say I run this regression. If I use this predict command, this is the one that said it doesn't allow me to like specify the values. Well, what did I want? Oh, because I already ran this. Hold on. Let's clear this out again. There we go. So it'll make predictions for every person in the data set, but it won't make like predictions for like my hypothetical person, right? Well, we can also use that predict command, and I think I showed this to you before. If I put comma residuals, it's going to not calculate just the predicted value. It's going to take the actual Y value, subtract the predicted Y value, right? It'll tell me essentially the error that my predictions were making for each individual, right? So I'm going to go ahead and do that. And that's going to be my error term for each observation. So what's one way I could check to see if my error terms have an expected value of 0? Well, what is an expected value of 0? A mean of 0, right? So if I use that sum function, I can look here and see, oh, e to the net 0.00000, I might have forgot a 0.2, right? This is basically a mean of 0. So there it looks like that main assumption that the expected value of my errors from this regression, given the x values, looks like it's 0. All right, so it looks like that condition is met. Right? Now, what I could also do here is not only do I want it to have an expected value of 0, how should it be distributed? So just like our coefficients, our errors, we're kind of assuming are distributed normally. I can use this hist function. This will give me a histogram. That's not perfect, but it gives me some idea of what the distribution of the, well, here doesn't look like my errors are quite normally distributed. Right? Now, the reason why might be I'm looking at something, that variable that I'm looking at, cigarette use, it's not truly continuous. It's got like discrete values. Also, I think, what's going to be true about cigarette use? I'd actually probably want to look at not just this histogram, but a histogram if the value is above 0, because there's going to be a lot of zeros in this data set where people just don't smoke, right? So I don't know, it's just another way I can kind of take a glance at what those errors are. But the really only assumption that we needed to have an unbiased estimate was that the expected value or the mean is 0. But using a hist function, it's a way to kind of check for normality in variables as well. So we talked about predictions. We talked about being imperfectly multicollinear. Next week, we'll kind of dive into some like random issues. We talked some about, I've already jumped the gun on some of them. We've talked about scaling variables. We've talked about standardizing variables. We'll revisit the adjusted R squared probably a little bit more. And then the only real new thing we'll do next week primarily is something called joint hypothesis testing. So we'll talk about joint hypothesis testing next week. I'll just really be rehashing a lot of the examples that we've been going through. And then the next week will be review and the exam. So one more week of new material, although most of it will be rehashing things we've already talked about. Other than that, start working on that third problem set early so you don't have to work on it close to the exam. Other than that, we'll see you guys on. Oh, I have a good one for you before we leave. Hold on. My wife would be mad because she helped me come up with this. Imperfect multicollinearity is like when you have two almost identical outfit options, but neither one really helps you slay. I don't know, because one of the standard errors is messed up. So anyways, fun, safe weekend. I will see you guys on Tuesday, okay?